Carbon Assessment Tools for Urban Development by Colin Beattie, Jess Bunning, Joanne Stewart, Peter Newman and Martin Ander. This study aimed to assist the understanding of current carbon performance and how carbon assessment can be mainstreamed in urban development. In doing this, the carbon emissions associated with 4 types of urban settlements in Western Australia are examined, reflecting how people interact with their environment. These include peri-urban development, urban redevelopment, mining camps and remote Indigenous communities. The issues discussed on carbon emissions for urban communities in WA are indicative of the challenges facing urban development world over, so lessons learnt from our research can be applied to similar locations around the globe. The global development industry has recently witnessed a transition from an interest in building assessment tools to tools that rate sustainability of entire developments. The shift of focus means that the carbon emissions of different design densities and mix, as well as the urban infrastructure, are all included in the assessment. There are currently 21 different precinct-based tools under development, according to the International Federation of Landscape Architects. However, these tools have yet to address all the carbon metrics inherent in the life cycle of a development. Rather, they offer frameworks for assessing the overall sustainability of a settlement. Thus, the precise nature of a carbon metric is lost in the broadly semi-quantitative and subjective nature of sustainability assessment. A carbon assessment tool is required which considers the carbon metrics for all the sources of emissions in the life cycle of an urban development. These are outlined in our studies framework, including the carbon emissions used in the materials of the building and infrastructure, carbon emissions used in the construction-deconstruction process, the electrical power and natural gas, the transport fuels, and the carbon emissions produced in the full water cycle, as well as the solid waste. The full life cycle is representative of the impacts on carbon emissions associated with the annual operation, manufacturing, and construction processes. The diagram illustrates how the sources within the metabolism of the development are interrelated. The determination of carbon metrics for the sources can enhance understanding on which responses are best suited for a particular development, and the impact and trade-offs that might occur to carbon emissions in the metabolic system through these actions. A detailed study of tools for measuring carbon was completed this year as part of the Australian Research Council Decarbonising Cities and Regions project. The results identified 2 very different tools that between them fulfill the majority of the carbon metrics required to be measured for the project framework covering the 4 case studies. CCAPPrecint is a modelling tool which is specifically designed to model various development options against a business-as-usual reference model. The tool has inbuilt algorithms that allow some modelling to be produced with very basic levels of data at the outset. e-Tool is a software program that calculates the embodied and operational carbon emissions of buildings and civil works. The tool is designed to calculate in detail the embodied carbon emissions attributable to individual buildings and structures. The tool is particularly suited to the remote small-scale villages of this study. The CCAPPrecint model is designed around 5 key performance indicators examined in separate modules. The Energy and Greenhouse module creates a ledger with data collected from the utility companies, providing records of gas and electricity supply and demand on an hourly basis throughout the year. The Embodied Energy module accounts for the one-off release of carbon emissions in the minerals extraction, manufacture, transport and assembly of materials constitute the residential dwellings in the infrastructure that comprise the precinct. The water cycle module examines the mains and alternative water demands of a precinct. The transport module calculates the carbon emissions from travel by precinct residents. The cost-benefit module draws on the design elements selected in the other modules, as well as local utility and transport tariffs, to provide an analysis of both total household affordability as well as the indicative capital costs for the selected green infrastructure. These 5 KPIs provide carbon metrics that respond to 4 of the 6 framework elements. However, 2 elements of the framework will need further investigation. These include carbon emissions of construction and carbon emissions associated with solid waste. Urban Development Case Study. The Curtin Coast Development Site covers 330 hectares of land to the south of Fremantle, of which 200 hectares forms prime development land and will have 4,850 new dwellings, 10,000 residents and 6,800 jobs, which aligns with the State Development Plan Directions 2031. The CCAPPrecint tool was used to assess carbon as part of the planning design process comparing parameters set by the district structure plan and for a high-performance alternative. It was very quickly established that the targets set by the DSP were easily achievable with relatively simple approaches, some of which would be expected in new developments anyway. So the bar was raised by hardening up the targets and modelling the proposal using a number of additional technologies that are associated with improved performance. The model returned significant performance improvements. The majority of costs with the upgrade from the Australian Building Code's 5-star requirement, which relates to the thermal performance of the building fabric. The majority of the capital costs associated with reaching these improvements are borne by the increase to 7-star and installing solar hot water. The high-performance case shows some remarkable step changes in performance. Transport emissions reduced by 36% from the Perth average and 3 times more effective than the district structure plan scenario. The original DSP did not include any targets for reducing embodied emissions, but with the simple substitution of part of the cement content associated with concrete construction with a recycled alternative, a 23% reduction in embodied emissions can be achieved. The energy performance increase steps up from a 38% improvement over the Perth average for the DSP to 55% for the high-performance model. This is primarily through a combination of low and zero emission electricity production on site, particularly through trigeneration. Water performance stepped up from 48 to 75% with residents responsible for 30 kilolitres per person per year in the high-performance case. And it is important to note that this also improved affordability in terms of 17% reductions that can be expected across transport and utility costs annually. So for an additional $900 capital cost per dwelling, some astonishing improvements in performance can be seen at a capital cost that will pay for itself in less than a year. Remote settlements case study. Remote settlements in Australia are often located far from towns and support services, so they're typically characterised by a high use of transport and therefore fossil fuel. They're also situated in harsh climates, which means energy is often required to maintain thermal comfort of residential and community buildings. Goods and services are often provided by external suppliers, increasing the transport requirement of a delivery to site. Mining camps are typically designed for a temporary lifespan to match the expected life of the mine. Workers are flowing in and out of the site on rotations of 1 or 2 weeks, so air travel is a common source of carbon emissions. There are over 1,000 Indigenous communities that are classified as remote or very remote in Australia. Over 50% of these communities rely on diesel-generated power for their main source of electricity. Over 50% also have water supply by bore water, which needs to be pumped from groundwater sources. About 75% of the communities have less than 50 residents and 9% have over 200. Research has shown these small remote communities can have better social and health outcomes than those based near towns. Therefore, it is important to determine how they can be maintained in a low-carbon configuration that meets their residents' cultural needs. Remote communities tend to have quite linear process systems with energy, water and materials being supplied by external sources over long distances. Residential and commercial buildings need energy for thermal comfort, food storage and appliance use, so need be as efficient as possible to reduce energy use. If waste is not recycled, it needs to be transported or taken to a landfill site, which again requires transport and fossil fuel use. The e-Tool software provides the energy and carbon calculations for embodied energy and materials, for initial construction and for replacement parts and maintenance. The construction process, including delivery of materials and energy required for operation of construction equipment and travel of tradespeople, can also be included. The direct energy used for thermal comfort, appliances and water heating need to be calculated separately, either by modelling or taking meter readings. These can be entered into e-Tool with the energy source, such as solar PV or diesel generator, for a carbon emission calculation. Water systems energy use can then be calculated in the same way, with a source entered into the tool to calculate carbon emissions. Transport during occupancy phases is not included in e-Tool, so fuel use needs to be calculated separately. Embodied energy of infrastructure, such as roads, can be calculated using the same principles for buildings by entering materials required and hours of equipment use. Waste emissions also need to be calculated separately, but simple infrastructure such as composting bin systems can be determined by modelling materials and construction processes in e-Tool. As actual case study data is still being collected and a hypothetical example was modelled using e-Tool. The 3-bedroom, 2-bathroom house has a brick veneer construction with concrete tile roof. It has a design life of 35 years and assumed to be close to trades and services for construction and maintenance. Operating energy use was derived from a study by Beale in 2006 of consumption by remote communities in the Northern Territory. The example compares two energy supply options. One was solar PV as the main source of electricity consumption, a solar hot water system and a diesel generated water supply. The second has supply be a community diesel generator and a solar hot water system. Diesel systems are assumed to have a 3:1 primary to direct energy ratio. The study by Beale indicated a mid-range of operating energy use of approximately 20 kilowatts an hour or 75 megajoules per day. This excluded hot water heating, which required a further 36 megajoules per day. Results from the e-Tool modelling show a significant saving of approximately 140 tonnes of carbon emissions over the lifespan of the building with a solar PV system installed. While the material requirements for the PV system are higher, the operational savings of carbon emissions are significant. This analysis excludes the transport related to delivering diesel to site, which would further increase the emission savings of a solar system. There is a critical need for improved understanding of carbon emission consequences of urban development as an entire metabolic system. There is a gap in the tools market for carbon metrics to monitor carbon emissions, and there is a need to establish quantifiable data on carbon emissions. There is a need also for a suite of tools so that the gaps identified in construction carbon emissions and waste can be closed by A. Identifying tools that can specifically address these gaps, or B. Creating tools specifically designed to address the shortfall. This improved knowledge of carbon emissions will help stakeholders understand mitigation opportunities and appropriate targets based on informed decisions of carbon consequences for delivering a portfolio of strategies for carbon reduction action. It will also help guide decision makers on their choices of infrastructure and various initiatives for particular settlements, and propose low carbon design choices for sites with similar circumstances. This paper has produced a framework to identify and measure the carbon emissions involved in the life cycle of a development, and thereby determine the full impact of the built environment. The research has shown that there are currently no tools available that meet all the framework requirements. There are a small number of tools that tackle one or more of the carbon emission sources set out by the framework, yet only 2 tools reviewed were designed specifically to deal with 4 of the 6 carbon emission sources. These are CCAPPrecintTM and e-Tool. Thank you.